Hey everybody, this is what we call in science a jug of vinegar. And as you can read from the label, it has been luted with water to 5% acid strength. I don't know what luted means, but anyhow, that acid in there is called acetic acid, and that is what we call a weak acid. And that's why you could drink vinegar, basically. I wouldn't recommend doing it. Let's go talk about what this thing's pH would be right now. Oh, diluted. The label got scratched off. Okay, let's go do some stuff. Well, hey everybody, hey, Mike here, and we are going to talk about acids, bases, and how they relate or cause the pH of a solution. And we're going to start simple. We're going to start with the simple things we call strong acids and bases. Those are the things that are completely broken up into their respective ions. So a little bit of review from Gen Chem 1. And we're going to do this all in the Brunstad style, except for sodium hydroxide here down below, which we can't. But a strong acid or base is broken up into either hydronium ion like this. So this nitric acid is going to protonate or put a hydrogen onto water to make hydronium ion. And straight arrow world here. No equilibrium. What the hell? Hold on. And I'm back. Turns out my light blew out a circuit and I needed to, never mind. Okay, so like we were talking about, strong acids and bases are completely dissociated. Now I can't do the Brunstad version with the sodium hydroxide, but you can see that it would be completely dissociated into OH-, which would make the pH go above 7, and unlike H3O+, which would make the pH go below 7. So, who are the cast of characters? The usual suspects are these sets, and there's more than these. They just start to become obscure. So your common acids that this is your stomach acid, strong acid HCl, nitric acid. Perchloric acid is a little bit explosive, so you probably won't work with that. Hydroiodic acid is what people make when they make meth, so you probably won't run into that. Sulfuric acid is your acid electrolyte in your car battery. Little asterisk by that because only the first ionization, 1H+, comes off in a strong fashion, and the second is like weak, which we'll talk about next. Strong bases, take an alkali metal which is completely soluble and slap an OH on it, and then you got a strong base. So these two here, magnesium hydroxide, which is what you find in Mylanta, the antacid, it just doesn't dissolve well in water at all. So that's why I put a little asterisk by it. So let's solve ourselves a problem, huh? Let's go ahead and solve this problem. What is the pH of 0.015 HNO3? So really, it's not that difficult, because what happens when 0.015 HNO3 hits water, you've got 0.015 molar H3O plus and 0.015 molar NO3 minus. So all I really need to do to figure out the pH is go ahead and take the minus log of 0.015. Now, just a little landmark action going on here, just so you kind of see. 0.01 would be a pH of 2, because the log of 0.01, 1 times 10 to the minus 2 is 2. This is a little bit bigger than that, so don't just blindly trust your calculator. But when you go ahead and you do your logarithm, 0.015, and you hit log, you get minus 1.8239. So that would be minus 1.8239. Now let me tell you a little bit about pH numbers. That has two significant figures. And of course, instead of saying that that's a pH of 1.8239, we're going to have to say that's a pH of 1.82. Why? Well, because that first number in the pH is not significant. It is because of how many zeros there are. It's a power of 10. So you only go as many decimal places as you do sig fig. So that's just a little bit of thing that might come up and up and up again. Whoop, here we go. Even though calcium hydroxide doesn't dissolve very well. Now what we're going to do is we're going to, you might have to go and replay a little Gen Chem 1 in your head. When this breaks into its ions, it's going to be a calcium 2 plus and 2 OH minuses. So what's going on here is that will be 0.080 molar, but this will be 0.160 molar, right? Plus X plus 2X. So now I need to take a negative log of that. And minus log of that, 0.160. This is the POH. POH. So let's go ahead, 0.160. I'm going to take a log. I get minus 0.796. So this would be 0.796 is the POH. Well, it didn't ask for the pH. Bases, POH. Bases get a bad rap. They're always kind of getting slighted. Like POH isn't what we use as a standard. It's pH. Now you got two things that you could have done here. That's the OH minus concentration. And you got two relationships. You got concentration of H3O plus times OH minus is always 10 to the minus 14. Go watch the last video if you need a refresher on that. Or if we took a negative log of both sides of this equation, pH plus POH equals 14. That means the pH is 14 minus POH. That means this pH of this particular example is 14 minus 0.796, which is 13.204, but I'm going to go to only 2 digits. It is 13.20 is the pH. Now, how do you check yourself before you wreck yourself? The thing that you could do that would be goofing it up, as we call in science, goofing it up. What if you stop here and you say, hey, that's the pH? Well, you go back and you say, does that jive with that? That's a base. pH of a base should never be below 7. And so you could say, oh yeah, I forgot, that's the POH, and I would need to take 14 minus that to get the pH. And so that would be a very strongly alkaline solution, by the way. And this would be a very strongly acidic solution. And so that's what you get with strong acids. You get a lot of bang for your buck with regard to how much H3O plus they make because they're completely dissociated. So next, we'll talk about weak acids and bases. Okay, folks, now, those usual suspects I just showed you, these folks here, the majority of acids and bases that touch your life are probably not those. You eat an orange, it's sour, that's citric acid. You marinate something, you make salad dressing, it's vinegar, that's acetic acid. You drink wine, it's tartaric acid. And so a lot of the acids that you ingest or produce in your body or bases are weak. Now that means partially dissociated, and by partially dissociated I mean not even close to 100%. That's just how it is. Now you don't have to really understand the why, but I could tell you that that's because there's some bond that is polarized that makes the H plus pop off is not as polarized as it is in like an HCl or something like that. So there's reasons for this, but we need K values because this is an equilibrium. We have a K constant. That's one of the things that determines the pH. And then you got the concentration, which we were just talking about with acids and bases that are strong. So here with weak, you got two variables. How concentrated is it? And what's the K value? Now you notice that little A, that means acid. So if we took a very generic look at how an acid works in the Brunstad style, you will see, we'll call this HA. This could be acetic acid, this could be hydrofluoric acid, but you see it always ends up putting an H plus onto water, double arrow, that's an equilibrium, and then making an anion here, A minus, and so products over reactants. We don't put water into a K when it's the solvent because that's just going to add a constant that will drown out all the other numbers that change. So don't put water in the bottom. We've got H3O plus, which causes the pH, and Ka. Where do you get these Kas? Oh, you go get yourself a table. Here's a bunch of Kas. And they were actually nice enough in this table to give you the reaction that goes along with them. But there's a bunch of K. Notice how small they are. And the less small they are, the more potent the acid. And so we're going to do an example next with what's in vinegar, which is acetic acid. So you need a K table of that. And then we got K table of bases. And that would be Kb, which is the same kind of format there. You have products over reactants, and this is one of the things you need is the value of Ka or Kb and the reaction, that's the R, and guess what? A Rice table. And so we're going to waste no time and use Ka or Kb to calculate the pH of, well, what's in vinegar? Actually, you know what? What the heck? Hold on a sec. I don't want to do 0.1 molar. I want to do what vinegar is. Then we're going to go ahead and we're going to calculate the pH of what vinegar is. Now vinegar, when you get it in the store, is a 5% solution. So that's 5 grams per 100 milliliters if you assume it's got a density of 1. That would be 50 grams per liter. And hold on, I got to go get my calculator. All right, I did a real quick, like a bunny calculation here. 50 grams per liter. Acetic acid, and there's two ways to write acetic acid, is about 60 grams per mole. I did that one quick. This would be 0.833 moles per liter. That's about how concentrated vinegar is. So what do? First, R, you got to write the reaction of it reacting with water. I'm using the newer style of writing acetic acid where it has an H something. Looks like more of an acid coming at you when there's always an H on most acids and it's usually on the left. The biologists like to write it this way. I'm not going to say anything bad about them today. And so that's the R. Guess what else we need? We need to go look up a K value, which is in our chart. Now your chart might not look like mine, it don't matter, they're all the same. But you will see that for acetic acid, 1.0 times 10 to the minus 5. 1.8, excuse me, times 10 to the minus 5. That's the K value of acetic acid. So I'm going to need that for later. Ka equals 1.8 times 10 to the minus 5. Okay, Rice table. Boom, 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 bada boom, boom. Boom, 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 bada boom. Rice table. R-I-C-E. So let's go plug in everything in. Now we're going to treat this like it came to equilibrium. 0.833. It's at equilibrium when you stick a pH meter in it. But 0.8833, 0, and 0. And then every one of these that disappears makes one of those and one of those. You know, this is why acid-base world is a little more tolerable than general equilibrium world. Everything's ones. But we're gonna get a little scary situation coming up here in a little bit, though. So at equilibrium, the concentration of acetic acid is 0.833 minus X, X, and X. So now we have to kind of go and remember what Ka is. Ka is the products over the reactants, but not the water. So it's H3O plus times the C2H3O2 minus concentration divided by the HC2H3O2 concentration. And that is 1.8, because I looked it up in the table, times 10 to the minus 5. So these things I'm underlining go all up in there. This is going to be X times 0.833 minus X. And now this is going to be a, oh no, it's the quadratic equation. Ah, no. I'm going to have to take this and multiply both. Nope, actually it turns out you don't, because I've got a little trick. It's called the 100 times rule, or what they call the small x approximation. And it goes a little something like this. I kind of worded it, paraphrase it. If the initial concentration is 100 times larger than Ka or Kb, X in the denominator is negligibly small and can be eliminated. Okay, this is going to be our friend. What does that mean? If K is so small, that means X is going to be small. There's not much product. Specifically, if this number right here is more than 100 times greater than that number, or you could do it the other way around. If this number is less than 100th of that number, but I like to do big number divided by small number. Now let me go ahead and do that. 0.833 divided by 1.8 times 10 to the minus 5. What do you get? You get 46,277. What does that mean? That means I can go like this. Squiggly equally sign. I love this squiggly equal sign. That means pretty much, I changed that to x squared. I hope I didn't lose you. Over 0.833. Compared to 0.833, x is small. And so now this simplifies things a great deal. This means 1.8 times 10 to the minus 5 is really x squared divided by 0.833. That means x squared is going to be 1.8 times 10 to the minus 5 times 0.833. Let's find out what that is going to be. So, using my good old calculator, 1.8 times 10 to the minus 5 times 0.833 is 1.499 times 10 to the minus 5. That's still x squared. Eye on the ball here. We got to get x, but we're not done when we take that square root and get x. X is just the way to the pH, 3.87 times 10 to the minus 3 molar. What does that mean? Now you got to go back and remember, what the heck did x even mean? X meant the amount of H3O plus produced in our rice table, and the acetate ion, but we don't care about the acetate ion. They're not asking about it, but that's what it is. And if you wanted to take 0.833 minus x, you would find out you basically get 0.833. Go ahead and do it if you want. You might get 0.832. Big deal. All right? Not going to change the value of K when you put it in. So now I got to remember I want pH that's minus log of 3.87 times 10 to the minus 3. So I'm going to take that number that's still on my calculator. I'm going to hit the log button, 2.41, but I need the negative of that. pH is minus 2.41, 2.41. Does that sound good? It doesn't sound that good. It's not as strongly acidic as that first example we did where we calculated the pH of 0.015 nitric acid, 1.82. This is a little bit higher, even though it's more concentrated. And so that's the kind of pH a weak acid produces, is something. And actually, to be honest with you, as far as weak acids go, acetic acid is a pretty strong weak acid. It's pretty potent, I should say. And so let's do another one. We haven't done a base yet that's weak. Let's go do that. All right, got 6 minutes left of film in my camera, so I'm going to try to finish this one in 6 minutes or less. All right, and so, oh boy, a base. Notice it's got nitrogen in them. A lot of the weak bases do. That's called methylamine. If you're a Breaking Bad fan, you probably saw the episode with that. And this is 4.4 times 10 to the minus 4 is what the table tells me Kb is. And so it even, you go and you write the reaction, CH3, NH2. The reason that nitrogen is in these bases is they are good at accepting H pluses from water. There's our R, and this would make CH3, NH3 plus, and then what really matters is it leaves behind an OH minus. And then the Kb of this, as I looked it up in the table, is 4.4 times 10 to the minus 4. Same procedure, folks. Here we go. ICE. 0.500, 0, 0, minus x plus x plus x. At equilibrium, 0.500 minus x, x, and x. See how they all kind of set up the same sort of way? And so now I'm going to go and put that all up in Kb. Kb is products over reactants, which is CH3, NH3 plus. Don't matter, that's not the part we're going to solve for anyhow. Times OH minus divided by CH3, NH2. That is all 4.4 times 10 to the minus 4. That is going to be x times x divided by 0.500 minus x. Uh-oh. Uh-oh. Where's my 100 times rule? There. Whew. Can we use the 100 times rule? I don't know yet. 0.5 divided, now I can tell you, that's 5 times 10 to the minus, I'm not even going to use my calculator. That's 5 times 10 to the minus 1. That's roughly 5 times 10 to the minus 4. This number here is about 1,000 times greater than that. So I can tell by looking at it, this is, you know, the powers of 10 are 3 powers of 10 different. That is x squared over 0.5. So now I'm going to go ahead and solve 4.4 times 10 to the minus 4 equals x squared over 0.5. Doesn't that make life easier, the 100 times rule? And so now x squared is going to be 4.4 times 10 to the minus 4. I'm really feeling my mojo with this problem because that's just 1/2. That's going to be 2.2 times 10 to the minus 4 is x squared. I just need a quick square root. 2.2 times 10 to the minus 4. Square root of that is now x. X equals 0.0148 molar. Okay, watch out. What does it mean? And how does it get us to the pH? That is the OH minus concentration. When I do a negative log of that number, that is not the pH yet. That is the pOH. Oh, I had it on my calculator. Why did I take it off? 0.0148 log is minus 1.82 minus negative 1.82. 1.82 is the what? pOH. Remember, when you're doing bases, you got an extra step in there. It's kind of a bummer, but 14 minus 1.82 is, I know I could do it in my head, 12.18. Don't get happy yet when you do the negative log. If it's a base, you got a further step when you have to go and realize that that number is the POH. And by the way, that's also a pretty potent weak. That's a pretty big number for a weak base. And so methylamine, that's, you know, it's, if it was 0.5 of a strong base, though, you'd be up at pH 13 point something, and, you know, it'd be much higher pH. But this has got a pretty big K. If you got a really, really, really small K, you're going to find yourself closer to pH 7. So practice bunches and bunches and bunches, folks. You have just had weak acid and base boot camp. And don't forget, you could use the quadratic formula. Why would you want to? 100 times the rule is making your life easy. Don't you wish there was other things like that in life that made things easy? Okay. Folks, I'll see you next time when things get slightly more complicated, but we're still back to rice tables with coefficients of 1. Take care. Cheerio. Shredded wheat. Wheaties, Cocoa Puffs. Bye.